C lambda equals e to the minus tau I. Okay. That is called, that tau is called the optical depth. It's a unitless number, and basically it's related to the opacity. Okay? How is it related to the opacity? Or in other words, what is the definition of the opacity? Okay. The optical depth is defined as the integral along the path length of the opacity ds. Okay, so you have some line of sight here, there's some gas cloud, okay, and you integrate from the face of the cloud to the end of the cloud, okay, and then you basically have some quantity that you call the opacity along that path length, ds. Okay, so you're integrating along that path length, and this is called the opacity. Okay, and what is the opacity? Okay, opacity, okay, at position S along here, okay, S along there, is the density of the gas times something called the cross-section. You're like, you just keep defining things in terms of new things. Well, trust me, it is useful. It gets useful. Okay? So there's a lot of terms you're learning here. Okay? Optical depth, tau, opacity, chi. Opacity is the density times the cross-section. Okay? Cross-section is defined as the power removed from the beam, okay, divided by the flux in the beam. Okay? The power is in units of ergs per second per centimeter squared. Okay? And the flux, power is ergs per second, energy per time, and the flux is ergs per centimeter squared per second. So what do you get left with? Centimeter squared. One way of thinking of it, people think of it in a geometric sense, that it's sort of the area of the absorbing atom or absorber. Okay? But it's really defined as the power removed in the flux. It's a function of wavelength. So what is this saying? It says that you have some atom in the gas, the light's coming through with a beam, okay? And at different wavelengths, let's say at this wavelength right here, there is a certain cross-section of absorption, okay? And you multiply that by the density of the number of atoms that are in the beam, that are doing the absorbing. Does that make sense? Okay, for any one atom, there's a cross-section for absorption. To get the total opacity of how much light gets removed, you multiply by the number density of the atoms that are doing that absorbing. Does that make sense? Okay. The units of this is centimeters squared, right? This is centimeters cubed, minus 3. This is centimeters squared. So this has units of centimeter to the minus 1. Basically giving you the rate at which photons are being removed from the path per centimeter. That's why it's called the opacity. You know, how the photon field is becoming weaker per centimeter through the gas. Okay? All right. Now you might be looking at all this going, but we're going to talk about each of these terms in more detail. And this is, like I said, this is the drink from the fire hose day. Okay. Okay. Now, it's very important you realize something. This is, I said it earlier that this was the density of the gas, but that's wrong. And I kind of purposely said it wrong so that I could correct myself now. It's not the density of the gas. It's the density of the type of exact element which is giving rise to that absorption line. Okay? Let's say, for example, that this is a Lyman alpha line. Lyman alpha is the n equals 1 to n equals 2 transition in hydrogen. Okay? Can ionized hydrogen give rise to a Lyman alpha line? I'm shaking heads no. Well, there's no electron orbiting the hydrogen, is there? If there's no electron orbiting the hydrogen, when that photon comes through, there's nothing to interact. So no. So we don't want to include any ionized hydrogen atoms. We only can include the neutral hydrogen atoms. Right? Oh, it's even better than that. Because in the gas, when you look at all the distribution of hydrogen atoms, some are going to be ionized, no electron. Going to contribute to absorption lines? Nope. No electron, no bound-bound transitions possible. Some atoms are going to be in the ground state where the electron's orbiting in n equals 1. Some fraction of atoms are going to be excited and the electron's going to be orbiting in the n equals 2 stage. Some atoms will be excited even more and they'll be orbiting, electron will be orbiting in the n equals 3 stage. Okay? Of all of that hydrogen, which are there's only one of those that can give rise to the Lyman alpha absorption line. Only those which have the electron orbiting in the ground state. Because why? Because Lyman alpha is from the n equals 1 to the n equals 2. So only hydrogen atoms in the gas that have their electron in the ground state can give rise to a Lyman alpha line. You can have ionized hydrogen, excited hydrogen. None of those are going to contribute. So what, if we're talking about a Lyman alpha line, what's that the density of exactly? Hydrogen, neutral hydrogen with the electron in the n equals 1 stage. Exactly. That's the density. So never think it's the density of the gas. Never think it's the density of all of the hydrogen. If that's a Lyman alpha line and it rises from the electron going from the 1 state to the 2 state, then it has to be all hydrogen that starts in the 1 state. Period. That's a really important point. That density is only associated with the transition you're looking at. You have to know the physics. Okay? If it was an H alpha line, okay, H alpha is absorption from n equals 2 to n equals 3. So, ionized hydrogen? Nope. Ground state? Neutral hydrogen? Nope. First excited level, n equals 2 state hydrogen? Yes. N equals 3? No. So it's only giving you a window on one type of element in one type of excitation stage. Each absorption line. So think about whenever you see an absorption line, you are only learning about one very, very specific atom in a given excitation state. Okay? Lyman alpha, that's from n equals 1 and 2. H alpha, that's from 2 to 3. Okay? All right. And it gets even more complicated. Let's look at my favorite, magnesium 2. Okay? Magnesium 2, written this way. Magnesium 2. This is singly ionized magnesium. That means it has one electron removed from it. Okay? There is a certain transition at around 3,000 angstroms that comes from magnesium 2, very famous. It's a doublet, actually. But it only comes from magnesium that's been singly ionized, and the electrons that are left over are in the ground state. That's it. So when you look at that absorption line in the spectrum, that's the only thing you can study with that absorption line. Singly ionized magnesium in the ground state. Pick another line. Singly ionized calcium in the ground state. Pick another line. Twice ionized carbon with the electron excited a little bit. It's very, very specific. So all those absorption lines are coming from only one specific type of thing that has that density times the cross section for that particular transition gives you the opacity, which is how rapidly the photons are removed from the path. Then you integrate over that per centimeter. Okay, this is path length is in centimeters, right? So how fast they decrease per centimeter, integrated over the path that they decrease on, it gives you what's coming out the other end. This is a unitless number per centimeter, integrated over centimeters, called the optical depth. And it only applies if you're talking about an absorption line to that specific ion in that specific excitation state. Okay, I really obviously want to make that point. Okay, so hopefully now these have started to come together a little bit for you. And then what you're looking at is light's coming through. Light at these wavelengths makes its way through, no problem. Light at particularly this wavelength, its intensity is decreasing rapidly, so that very few of those photons make it out. The optical depth is high. The amount of light that passed through is low. Okay, so you see the dip. Okay. All right. Everybody probably has had enough for one day, but we have a few more minutes to go. Okay. Okay. Is a combination of many all the physics of the gas. Okay. Well, this number here depends upon a lot of things, because this could be an ionized ion in a doubly excited state or something like that. So that depends upon the physics, right? So there's some physics hiding in here. Temperature, density, photon field. Okay, everybody with me on that? Same thing with the cross-section. Part of that cross-section is the actual atomic physics. But part of that cross-section depends upon whether the atoms are moving toward the light beam or away from the light beam, the Doppler effect. Okay? So basically, if you come down to the bottom of this page here, the final cross-section can be what's called alpha natural. That's just from the atom and atomic physics. Convolved with the thermal broadening, convolved with any turbulent broadening, combined with, I've got collisional broadening, which is really pressure broadening, and combined with rotational broadening, all convolved. That's an integral of convolution. You probably are like, why would you ever want to study spectra? This is impossible. You can't learn anything from spectra. But it turns out you can. How do you think we know what we know about the universe? All right. So this cross-section, we'll be talking about throughout the course each one of these terms that go into the cross-section, okay, and how they're convolved together. And trust me, you don't have to do anything that complicated for the atmosphere model. The atmosphere model is like bare bones simplified. There won't be any radiative transfer well, it's what's called gray radiative transfer, and it turns out to just be like, 2 lines, 3 lines of code. It's very simplified. Okay. Okay. So I just want, it might be worth, I'll tie these 2 videos together. It might be worth to go back and, I don't know, in 3 weeks from now, come back and look at this, because it's like, you'd be like, oh, he just told us the whole semester in one class without giving the details. All right, the last thing I want to do is introduce to you something called the column density, and then when we come back, I'll be ready to show you the spectra on the next page. Okay. again, this is one of those things that I didn't discover until I was with my PhD for several years, how easy this is to write down. But we're going to start with tau of lambda is equal to the opacity integrated over the path length that the light travels through the gas. Okay, that we said was equal to the number density of that particular absorber, meaning singly ionized calcium in the ground state, or etc., times the cross section. Okay, basically replace that with the density times the cross section. Now, if the gas is well behaved so that the properties of the gas don't change along the line of sight, okay, so here's your gas cloud, here's your line of sight. What I'm saying is maybe the density can change, but let's assume that the temperature of the gas doesn't change and the atoms, the internal atomic physics of the atoms won't change depending upon where they are in the gas. You buy that one, right? Okay. So what happens is that we can take alpha out of the integral and say, well, the atomic physics or the thermal broadening is not changing through the long line of sight, so we can pull that broadening and cross-section out of the integral, and what we're left inside the integral is the possible variation in density along the line of sight as we integrate along that line of sight. Okay, this can be written as a column density, N. Okay? And that's where that comes from. And so what we can do then is we can write tau as alpha times N. So I'm just going to go back up here, bring it back around, and say that we can write this as N times alpha lambda. Okay, so in other words, tau equals N times alpha lambda. Okay. Now you might be saying, well, all you're doing is hiding physics into a number. And it's true, we are. Because in reality, guess what, folks? We never can do that integral. No matter what level of information you get from the light, you can't do that integral. Now, you can make a model of the star and the atmosphere, and you can, in your model, you can get out a profile of the density with path length or something like that. And then in your model, you can integrate it, and you want your model to integrate out, so guess what it gets you? This is atomic, so you've got that information. You don't have that. All you have is this. But, okay, if you can know what this value is down here, then you can measure that. From that, you've got N times alpha. Alpha is just atomic physics, that doesn't change. You get that saying, oh, that's from the physics of hydrogen, for example. All you have left is that. So you make a model, and in your model you get this, and then you do your integral in your model, and you hope that this integral gives you that, and then you say, hey, my model fits the data. I've possibly learned something here. Something like that. Okay. Okay, so that is the definition of the column density, and that gives us our final last expression that you'll see a great deal, which is I lambda over IC lambda is equal to E to the N alpha lambda. Okay. So from the spectrum, we can measure N. Then from modeling, we can measure N and try to match them. But this only gives you information for one absorption line that comes from one element in one excited state and one ionization condition. And you've got a spectrum full of many lines from different elements, from different ionization stages, and different excitation stages. Okay? And you have to match all of them simultaneously to your model. That's a little trickier. Okay. So now you know what the whole course is about. Measure the light, get the column density, make a model, match your column density. And hopefully, oh, did I say that to get this right, you need to know the temperature and the density and the chemical composition because you're doing multiple lines, and you need to know the radiation field because that also governs the ionization balance and the excitation balance. So you have to put all that physics in there. How the atoms ionize, how they get excited, how they recombine and the electrons get back onto them, the balancing of all of that in order to have that final physical model from which you can say, okay, for this line, the run of density in my model does this. Do I get out the column density for that line? Yes or no? Okay. You've got to make this model balanced so that you get out the column densities for all the different lines from all the different elements at the same time. And it's a big physical mess. So if you know how to model gas physics, you can do it. But what I'm hoping you're doing is you're walking away going, okay, I get it. There's a lot of gas physics. Electrons getting back on, electrons getting knocked off, electrons being excited, and all of that balanced with all these metals and all these different absorption lines, and you can actually try to get a handle on this mess from that spectrum.